Hello everyone and welcome to my video on selections. My name is Darren from Maffs Guru, my little corner of the interweb where these videos and downloadable lesson notes and VCAA questions and so much more are available to hopefully help you smash maths. Now behind me are my learning objectives. Did I say I was Darren? I think I did. My learning objectives: understand what it means to be a selection, how to find the number of selections which might be made, find selections of any size, use Pascal's triangle, and understand what Pascal's identity is. And this is relatively new stuff, but is building on the previous two videos that I have just recorded and again are on mathsguru.com. So please head over there if you want to. It's absolutely free to sign up. So previously, the order was important, all right? And by that, what I mean is if we had the three letters A, B, and C, for example, we have A, B, and C, then A, B, and C would be one order if we had three letters and three places to put them. And then C, B, A would be another one. And we would continue going on. And we would know that there would be 6 different outcomes. Why? Because we got 3 choices for the first, 2 choices for the second, and 1 choice for the third. But what if we just wanted to know how many ways there are of grouping those 3 letters? And they'll actually say that A, B, and C and A are actually the same. We don't care about the specific order the letters are in. We just want to know that we've got groups of A, B, and C. That's very much what this video is going to do. And as I say here, I would learn my ABCs again, but if I have to sing the ABC song one more time to my daughter, I think I'm probably going to cry. All right, it's really not fun after a while. All right, so let's say I'm just going to deal with A, B, and C and consider how many groups of 2 I can make with those letters. Now, in that situation, I'd have AB, BA, AC, CA, BC, and CB. All right, so I'm fairly sure that those would be my 6 outcomes. And again, just to check, how many letters have I got? I've got 3 for the first, 2 for the next, 6 outcomes. Right, but at the moment in time, it would appear that an order seems to be important here, yes? That AB and BA are 2 different selections, 2 different choices I can make. What if, in fact, the order wasn't important and the fact that I've got B and A and B, they are the same, all right? So I've got those 2 letters filling those 2 spots as just one choice. Those would therefore be the same. And therefore those would be the same, in which case I'd now be down to 1, 2, 3 different ways of grouping those letters A and B in just 2 spaces again. All right, so again, order's not important in that situation. What about 4 flavors of ice cream? Vanilla, chocolate, strawberry, and caramel, or if you're in America, caramel, are available at the school canteen. How many different double scoop selections are possible if 2 different flavors must be used? All right, so again, how many different double scoop selections are possible? Now, again, I could turn around and say there would be vanilla and chocolate, and then vanilla and strawberry, and vanilla and caramel, and I could do chocolate and vanilla, and chocolate and strawberry, and chocolate and caramel. Oh, sorry. But basically, in that situation, this one here and this one here would be exactly the same. And what we've realized there is it would be pointless using that all together. So we're now going to try and work out, well, how many different combinations we can get here where the order isn't important, that a vanilla and a chocolate is exactly the same as a chocolate and vanilla. So we're going to have vanilla and chocolate. We got vanilla and strawberry. Can't spell. And we got vanilla and caramel. We'd have chocolate and strawberry because I haven't got that one yet. I'd have chocolate and caramel, and then I'd also have strawberry and caramel. And in which case, that would suggest I've got 6 different ways of choosing 2 scoops where the order of the scoop doesn't really matter. Now we're going to start using combinations, all right? When we make choices without regard to order, we call them selections or combinations. That's different from arrangements or permutations, as per my previous video, selections or combinations. And whereas before we used NPR, all right, that's the number of permutations, NCR is the notation we use where order isn't important. We're just trying to work out how many ways we can put n objects in R numbers of groups, okay? Or the size of each group. Right, there is a formula. NCR is basically to NPR divided by r factorial. We know that NPR is basically n factorial divided by n minus r factorial. So we're just basically adding that r factorial. And I'm going to try and work out why that is now. So if I look at the idea of the Olympic rings, we know that initially the example said that there were 8 colors that the painter had to work from, and there are 5 rings. Now beforehand, if you remember the example from a previous video, we would have done 8 times 7 times 6 times 5 times 4. That would have given me the number of rings, or the number of different choices, which was 8 factorial divided by 3 factorial. The problem was there, though, that red, orange, yellow, green, and brown, yellow, orange, red, and green basically would have been 2 different arrangements. Well, we're now not bothered. The fact of it is, we've got those there. You know, we got the 5 colors repeated. How many different ways would those 5 colors be repeated? Well, again, we can go back to our general idea that there would be 5 choices, 4 choices, 3 choices, 2 choices, and 1 choice, or 5 factorial. So if we are now trying to reduce this by getting rid of all of those duplicates and saying they are the same, then I would want to divide by that 5 factorial to get rid of those number of choices. Okay, so again, a different way of thinking about it. There's my n factorial. There's my n minus r factorial, which is 3. And there is my group size in that terms. And what we tend to notice is those 2 values add to make that value as well. So put that in your summary book. Hopefully this is making sense. Right, what about the 4 flavors of ice cream are available? How many double scoop selections are there? So we've got r is equal to 2, and we've got n is equal to 4. So NCR is going to be n factorial divided by n minus r factorial, and then r factorial. And again, 4, 2, and 2 add together. So 4 factorial is 4 times 3 times 2 times 1. And again, I can do 4 times 3 times 2 times 1. If you're ever in a bind, 2 times 1 times 2 times 1. Well, okay, nicely, those 2 cancel each other out. And 2 times 1 basically is 2. That goes into there 2 times, which gives me the 6 that we were looking for. And again, I could have slammed that into my calculator if I'd wanted to. And yes, there are calculator functions that can do this for you. Let's just show that while I'm here. So menu, probability, let's do combinations, NCR. The first value you put in there is the value of n. And so that would be 4, 2, hit enter. And out comes my 6 different selections I can have. Okay, fabulous. A team of 3 boys and 3 girls is to be chosen from a group of 8 boys and 5 girls. How many different teams are possible? Now, this is going to go back to my addition and multiplication rule from the first section, that I'm now looking for choices. I've got to choose a group. I've got to choose the 3 boys first and then the 3 girls. Well, how many ways are there of me choosing the boys where the order doesn't actually matter? Well, how many boys have I got? I've got 8. And how many am I choosing from? 8, choose 3. So that's the number of boys I'm going to end up. So I tend to write boys, and then I've got girls, and I've got how many girls? 5 girls, and I need 3. So 5, choose 3. That's going to be 8 factorial divided by 5 factorial, 3 factorial. That's going to be 5 factorial divided by 2 factorial, 3 factorial. All right, and again, because I've got a choice, all right, because this is going to be the number of boys I could choose, and that's going to be the number of girls I could choose, I would then multiply all that together to give me my final answer. Ooh, there we go. So doing that on my calculator, as in I'm just going to do 8C3. So if I copy that down and then do 8, choose 3, I get 56. Writing in highlighter. And then 5, choose 3 is going to give me 10. So in which case there would be 560 different ways of choosing 3 boys from 8 and 3 girls from 5. That is a lot of ways, yo. Now, selections of any size. What would happen if we need to count all the possible combinations of any size from a group of n objects? Right, we are basically told, and I'm going to say we are told, for selections of any size, we get this here. Now, there are two ways of thinking about this. And so what I want to do is try and unpack that now as sort of a bit of an aside for those of you who are out there who are interested. Right. Imagine I've got three books. I've got A, B, and C. And I can choose to have no books, one book, two book, or three books from that choice, right? So that is the number of ways I could sort of choose. I can choose none, I can choose one book, two books, or three books. So if I'm going to choose no books, that would be 3, choose none, right? How many ways are there of choosing no books? Well, in fact, there's only one way. Why? It's sort of self-explanatory in that situation. I could choose one book. So how many ways of me choosing, one book from 3? There would be 3 choices. I could choose 2 books. And again, I'm using a bit of a shortcut in my head here. I'll come back to how I'm doing that in just a moment. But again, how many ways are there me choosing 2 books from 3? It turns out there's 3. Or I could choose all 3, in which case there is only one way of doing it. Now again, in that situation, just to sort of narrow it down, there'd be no books there. That would be A, B, or C. That would be AB, AC, or BC, and in which case that would be A, B, and C. So those are, if we count them up, my 1, 2, 3, 4, 5, 6, 7, 8 different ways of choosing those selections. Yes? Now again, what is the total number of ways of doing it? All right, because that's what they're looking for. If I was looking for the total number of ways of choosing no books, one book, two books, or three books, I'd obviously want to add all those together, which is what I've done here. So if I add all those together, I get 8. Now, looking at this another way, if I look at the idea that, well, how many ways are there of me choosing book A? Well, there's 2 ways. How? Because I'm either going to choose it or I'm not. How many ways are there of me choosing book B? Well, there's 2 ways, because I'm either going to choose it or I'm not. How many ways are there of me choosing book C? There are 2 ways. Why? Because I'm either going to choose it or I'm not. Oh, and that's good because these now match up. But what we get is that can actually be written as 2 to the power of 3. So therefore, we can say that 3C0 plus 3C1 plus 3C2 plus 3C3 is equal to 2 to the power of 3. And sort of packing this now, if this is my value of n, and that's my value of n, I now know from NC0 all the way up to NCM, that's going to be equal to 2 to the power of n. Now, how are we going to use this? Nick is making an invitation list for his party. He has 7 friends to choose from. Lucky Nick, I don't. Have you subscribed to my YouTube channel yet? If you could, massive. Just tells me you're watching. If he may choose to invite any number of friends from 1 to 7, because he's obviously not going to invite nobody. So that's the first trick here. How many possible party lists does he have? Right. And it says here, assume he's going to invite at least one person to his list. So he's got 7 friends. How many ways are there of him choosing one of them? 7C1. How many ways are there of him choosing 2? And 3? And 4? And 5? And 6? And 7? Let's do that properly. 7, choose 7. Now again, I could put that into my calculator, but hold on, that looks suspiciously similar. Because if I did 7C0 on here, then we would now know that that would be 2 to the power of 7. Because we've decided from previously, if I take 7C0 all the way up to 7C7, that's going to be 2 to the power of 7. But he hasn't got this, right? That's not currently in there. So I'm going to take that away from both sides, which gives me 7 choose 1 plus all the way up to 7 choose 7 is going to be equal to 2 to the power of 7 minus 7 choose 0. And there are certain important ones that you need to use. And 7 choose 0, anything with a 0 down here is always going to be 1. So it's going to be 2 to the power of 7 minus 1, which again, I can put into my calculator. I absolutely know that 2 to the power of 7 is 128 from my computer programming days. So that's basically 128 minus 1, which is 127 ways. So there are interesting questions that I quite like here with regards to combinations. Now, Pascal's triangle and the identity. Pascal's triangle is a great way of working out combinations. And for those of you who know Pascal's triangle, the first numbers are 1, the next numbers are 1s, and then it goes 1, 2, 1, 1, 3, 3, 1, 1, 4, 4. Now, to get to each successive number, you will notice that there is sort of a pattern to this. If I do this one plus this one, it gives me the 2 in the middle, all right? 2 plus 1 gives me the 3 in the middle. 3 plus 1 gives me the 4 in the middle. 3 plus 3 gives me 6. 6 plus 4 gives me 10. So I can now go straight to my next line of Pascal's triangle. It always starts with a 1 and it ends with a 1. I'm now going to take 1 and 5 and add them together. It's going to give me 6. I'm going to add 5 and a 10 together, and it's going to give me 15 and 20 and 15 and 6. Now, you may have met this before with binomial expansion, because this is another way of getting the coefficients of our expansions. But again, another way of doing this is that this here is actually 0C0. This one here is 1C0 and 1C1, 2C0, 2C1, 2C2. And so what Pascal said is this. And it looks a bit confusing initially. NCR is equal to n minus 1 CR minus 1 plus n minus 1 CR. Now what I'm going to do is actually choose a value. So let's take n equals 5 and r equals 2. So let's choose n equals 5 and r equals 2. So what this is now saying is that 5 choose 2 is equal to n minus 1, which is 4 choose 1 plus 4 choose 2. Let's just check if that's actually right. So if I highlight my 4 choose 1, which is that one there, and my 4 choose 2, oh my goodness, that's what that is. So realistically speaking, it's just trying to tell you there in a way more complicated way that we can add the two previous numbers to make the successive number there. All right, lot for that chapter, a lot of practice needed. Did we understand what it means to be a selection? Yes, that's where order isn't important. Find the number of selections which might be made. Yes. Selections of any size. Yes. Pascal's triangle and Pascal's identity. Hopefully it's been useful. If it has, leave a message in the comments on YouTube if you're watching it via YouTube. Otherwise, I don't know, send me an email or just let people know that it's been useful. Subscribe if you can, and hopefully I'll see you in another video. Until then, take care. Bye-bye.